Hello everyone, let me start today's class. Today we will talk about input and output devices, often just called IoT devices. In this lecture, we will learn how IoT devices are connected to computer systems and how the operating system communicates with them. Before we start, let's quickly look at the overall structure of the course. So far, we've studied virtualization focusing on the CPU and main memory. Now we have two major topics left. One is concurrency, and the other is persistence. Before we dive into concurrency, we'll first cover persistence. And today we'll start this issue by talking about storage devices. And here is an overview of today's lecture. We'll first look at how IoT devices are structured and how the operating system interacts with them. And then we will learn about methods for I/O communication like polling, interrupts, and DMA. After that, we will talk about file system abstraction for I/O devices, and we will look at two storage devices like hard disk drives and solid-state drives. Okay, then let's start with I/O devices first. Basically, I/O stands for input and output, and it is very critical for a computer system to interact with the outside world. Without I/O, a computer system cannot receive any input from users or send any output to devices like screens or storage. But I/O also brings up some important questions. How should we connect I/O devices to the system? What general methods should we use? And how can it do this efficiently? We will explore these issues one by one in this lecture. And next, this slide shows the base structure of how I/O devices are connected in a computer system. As you can see, the CPU is connected to the main memory by using a high-speed memory bus. This kind of bus is fast but also expensive. So to reduce the cost, system designers utilize hierarchical bus structure like this figure. I mean, instead of connecting all devices with high-speed buses, they use different types of buses depending on the device's speed. For example, fast devices like graphic cards are placed close to the CPU and connected through general I/O bus like PCI. General I/O bus is faster than slower than memory bus, but faster than peripheral I/O bus like SATA or USB. And these slower I/O devices like keyboards or printers are connected through slower and cheaper buses like USB or SATA. By doing so, this design helps balance performance and cost in modern computer systems. Okay, then let's talk about how I/O device is structured. Basically, typical I/O device has two main parts. The first part is a hardware interface, which lets the operating system control the device. And the second part is internal components. This can include a small CPU, some memory like DRAM or SRAM, other hardware-specific chips, and firmware to control these components. These internals are different depending on the device, and the operating system talks to the device through this hardware interface. But it doesn't need to know the details of how the internals work. The hardware interface of I/O device usually includes several registers. First, there is a status register, which shows the current state of the device. For example, whether it's busy or ready. And secondly, there is a command register, which lets the operating system tell the device what to do. And there is a data register, which is used to send or receive data. So by reading and writing these three registers, the operating system can fully control the behavior of the I/O device. Okay, on the next slide, here is a simple example of how the operating system can communicate with the I/O device by using its registers. First, the operating system checks the status register in a loop until the device is not busy. And then it writes data to the data register and sends a command to the command register to start the operation. Finally, it waits again until the status shows that the device has finished the requested operation. So this pattern is very common in device interaction. And actually, there are several methods for these three types of interaction, like status checking, data transfer, and device control. In the next few slides, we'll take a look at these specific methods. Okay, then first, we will see two methods for status checking, polling and interrupt. In polling, the operating system keeps checking the status register over and over until the device is ready. Let's look at this figure. First, task 1 is running on the CPU, and then it requests I/O operation to the disk to read some data. Then the operating system simply spins, polling the status of the disk device repeatedly until the I/O operation is complete. And this situation is indicated by these characters P. And after handling this I/O operation, task 1 can resume again. So this method is very simple and easy to implement, but it has a big downside. That is, it wastes the CPU during this time. I mean, the CPU just wastes during this time doing nothing useful while checking the device. Instead, it would be better to let the CPU switch to another task while waiting. That's exactly what interrupt-based I/O does, and actually, I've explained this concept when I talked about limited direct execution model. To explain again, in the interrupt-based I/O, the operating system doesn't keep checking the device. Instead, it puts the I/O process to sleep and switches to another process. Let's take a look at this figure. Task 1 requests I/O operation at this point, and the operating system switches to task 2 on the CPU. That is, the operating system doesn't wait for the completion of the requested I/O. And when the I/O device finishes its job, it sends an interrupt to the CPU at this point. Then the operating system wakes up the task 1 and continues the execution of task 1 again, like this way. So this method allows both the CPU and I/O device to be used efficiently. I mean, the CPU doesn't waste time waiting. This is the basic concept of using interrupt. Okay, then now let's compare polling and interrupts. At first glance, interrupts seem better because they avoid wasting CPU time. But interrupts are not always the best choice. If the device is very fast, interrupts can actually slow down the entire system. That's because context switching is a few expensive. So here is a rule of thumb. If the device is fast, then polling can be more efficient. But if the device is slow, then it's better to use interrupts. In practice, many operating systems follow this rule. And next is related to methods for data transfer. One way to do this is called programmed I/O. In this method, the main CPU is responsible for moving data between memory and I/O device. This means the CPU must read its piece of data from memory and write it to the device, or vice versa. Let's take a look at this figure. When task 1 requests I/O operation to write some data at this point, the operating system should copy the data from memory to disk during this time. This is programmed I/O. And in this case, the CPU spends a lot of time just copying data, which can slow down the entire system, especially for large transfers. To solve the problem of CPU overhead in programmed I/O, we can use DMA, which stands for Direct Memory Access. DMA is like a special hardware controller that takes care of copying data between memory and I/O device. To perform data transfer, the operating system just informs the DMA controller where the data lives in memory, how much data to copy, and which device to send it to. After that, the CPU can execute another task during this data transfer. Okay, then let's take a look at this figure. When task 1 requests I/O operation, the operating system set up the transfer by communicating with DMA at this point. After that, DMA will copy the data from memory to disk on the behalf of operating system. And during this time, task 2 is running on the CPU. That is, we can avoid the CPU waste in this scenario. When the transfer and I/O operation is finished, then the DMA controller sends an interrupt to notify the operating system at this point. Then the task 1 can be resumed again like this way. So by doing so, we can improve CPU utilization, especially for large data transfers. This is the strong point of using DMA. So how does the operating system actually communicate with I/O device? There are two main methods. The first one is using I/O instructions like in and out instructions on x86 systems. These instructions let the operating system access specific device registers. And the second method is memory mapped I/O. In this method, the I/O device registers are mapped to specific memory addresses. So we can access these device registers as if they are in the memory locations. This means the operating system can utilize normal memory instructions like load or store to read from or write to the I/O device. Actually, these two methods are used in modern systems. Typically, different I/O devices often have different interfaces and features. And in this situation, we want to use general file system that can work on top of various I/O devices. So how can the operating system support them in a consistent way? The answer is abstraction. By creating a standard interface, the operating system can hide the details of its different device. For example, if we want to build a file system that works with SCSI disks, ID disks, USB keychains drivers, and so on. In this case, abstraction can allow the operating system to handle these devices in the same way. This is the power of abstraction provided by operating system. To this end, the operating system utilizes file system abstraction. Let's see this figure. There is an application layer on the top of this file system stack. An application can request I/O operation by using these standard API functions. Then the file system handles this request by sending some block read or block write operations to lower layer. That is, the file system doesn't need to know the exact type of storage device it's using, whether it's hard disk, SSD, or USB drive. Instead, the file system performs I/O operations by communicating with a generic block layer. Then the generic block layer communicates with a device driver using this interface. This interface can be specific to I/O device. Then what is the role of device driver? Basically, device driver is a special software component of the operating system that controls its I/O device. And it is required to define a standard interface to expose device functions. For implementation, some drivers are statically linked into the kernel, some are selectively loaded at boot time, and others are dynamically loaded by the user request, especially for hot pluggable devices like USB. One big challenge is that there are many types of devices, and each device usually needs its own driver. So managing all of these drivers is a major part of operating system development. As mentioned before, abstraction is very powerful, but it also includes several limitations. For example, if a device has special capabilities, these capabilities may not be used because the general interface doesn't support them. Also, device driver make a large part of the operating system code. In fact, more than 70% in many systems. And device drivers are often a major cause of critical bugs and system crashes because they are written for many different types of devices by different vendors. Nevertheless, abstraction provides many benefits for I/O device management. So the operating system still heavily relies on abstraction. Okay, then this time let's take a closer look at real storage devices, starting with hard disk drives. Basically, hard disk drives have been the main type of persistent storage in computer systems for many years. Each drive contains a large number of sectors, and each sector holds 520 bytes or 4096 bytes of data. And we can think of the disk as a large array of numbered sectors. If the total number of sectors is n, then the numbered sectors will be from 0 to n-1. So the operating system can read or write to any of these sectors to store or retrieve data. And next figure shows the architecture of hard disk drive. Basically, the hard disk drive is an electromechanical device, which means that it has both electrical and mechanical parts. First, it includes spinning platters that store data, an arm that moves across the platters, and a read-write head at the end of the arm. So through this head, we can read some data from the disk or write some data to the disk. This means to access a specific sector of the disk, the platter should be rotated and the arm should be moved to the correct position. And there is also a disk controller and buffer which handles the communication between the operating system and hard disk drive. And the host interface connects the hard disk drive to the rest of the system, usually through SATA or another bus. When accessing data on hard disk, three steps are involved. The first one is seek, which means the disk arm moves to the correct track on the platter. And next is rotation, which means we should wait for the desired sector to rotate under the read-write head. And finally, we have the data transfer, where data is read from or written to the surface. So each of these steps takes time and they will affect the overall performance of the hard disk drive. For example, let's see this figure. To read the sector 11, the arm of the disk should be moved to this track, and then this platter should be rotated until the sector 11 is placed under the read-write head. And then the read-write head can read some data from the sector 11. So this is basic behavior of a hard disk drive. The performance of hard disk depends on three factors. One is seek time. Seek time means the time it takes to move the arm to the correct track. And it is one of the most costly disk operations. And another factor is rotational delay, which means the time we wait for the desired sector to spin under the head. And it depends on RPM, which stands for rotations per minute. A common hard disk devices have 5,400 or 7,200 RPM. And the last factor is the transfer time, which means the actual time to read or write the data. So we can calculate I/O time through this formula, that is by adding these three factors. And the rate of I/O is equal to the size of data transfer divided by I/O time. To improve performance of hard disk, the operating system uses disk scheduling. The disk scheduler decides which I/O request to schedule next. It tries to reduce the overall delay by considering both seek time and rotational delay, because these two things are usually the most expensive. And there are several disk scheduling algorithms, and we will see one by one. The simplest disk scheduling algorithm is first come first serve. In this method, requests are handled in the order they arrive, so basically this is fair and easy to implement. And it works fine when the system is not very busy. But if the requests are spread out across the disk arm may have to move a long distance back and forth. causing long seek times. For example, let's see this figure. I suppose that there are several I/O requests like this sequence, and its number represents a sector number requested by its I/O operation. And I assume the disk head is placed on the sector 15.3. Then in this case, the head moves like this path according to FCFS rule. And it makes seek distance very long. This is the problem of first come first serve. And next is SSTF, which stands for shortest seek time first. This algorithm chooses the request that is closest to the current position of the disk arm. By doing so, it can minimize seek time. It's similar idea to the shortest job first algorithm in CPU scheduling. So SSTF can significantly reduce average seek time, but it has some downsides. That is, it may cause starvation. I mean, some requests, especially those far away, might be delayed for a long time. And this algorithm tends to unfairly prefers middle sectors. So when applying SSTF to the previous example, like this figure, it can reduce the seek distance effectively compared to the first come first serve algorithm. Another popular algorithm is scan, which is also known as elevate algorithm. In this algorithm, the disk arm moves in one direction, servicing all requests along the way. And when it reaches the end, it reverses direction and continues servicing requests. By doing so, it can avoid starvation theoretically, because every request will eventually be reached as the arm moves back and forth. However, wait times are not uniform because this algorithm tends to favor middle sectors. Okay, for example, if the head starts at sector 15.3, then the head will move this direction first. And then if it reaches the end, then it will move the reverse direction to handle this request. So this behavior is similar to elevator, and this is the reason why this algorithm is called elevator algorithm. And F-scan is advanced version of scan. The key idea is that the scheduler freezes the request queue while the disk arm is sweeping. This means it only services the requests that are already in the request queue when the sweep started. So this approach helps avoid starvation, especially for requests that are far from the current head position. And C-scan is a variation of the scan algorithm. Like scan, the arm moves in one direction and services all requests along the way. But when it reaches the end, it jumps back to the beginning without servicing any requests on the way back. And then it starts a new sweep in the same direction. For example, if we start at 15.3, then the head will move in this direction. And when it reaches the end, then the head will return to the beginning point without handling any request. After that, it will start a new sweep like this way. This is the behavior of C-scan algorithm. By doing so, this gives more uniform wait times compared to scan algorithm, especially for the caches near the edges. And both scan and C-scan are referred to as the elevator algorithm because their behavior is similar to elevator. Now let's move on to SSDs, which stands for solid state drives. Unlike hard disk drives, SSDs have no moving parts. Instead, they are built using transistors like memory and store data with a technology called flash memory. Flash memory is a type of non-volatile memory which keeps data even when power is off. Because there is no mechanical movement, SSDs are much faster, quieter, and more durable than hard disk drives. For these reasons, SSDs have become much more common in modern systems, especially in laptops, smartphones, tablets, and something like that. SSDs are now often used instead of hard disk drives. Okay, then let's take a closer look at how flash memory works. Each flash memory cell is basically a transistor with a floating gate, like this figure. As you can see, this floating gate is completely surrounded by oxide layer, which keeps the electrons trapped inside. When electrons are stored in the floating gate, it changes the state of the cell. This is how data is stored. For example, if some electrons are stored in the floating gate, then the cell represents 0 bit, and otherwise the cell represents 1 bit. So the key advantage of this structure is that the electrons can stay trapped for many years, even without power. That's what makes flash memory non-volatile. Okay, then now let's look at how flash memory is organized logically, especially in NAND flash. NAND flash is commonly used in SSDs. And basically, flash memory is comprised of several cells, and a group of cells makes a page, and a number of pages makes a block. So the exact size of block or page depends on technology, but they are getting larger over time. And most operations in flash memory happens at the page or block level, not at the byte level. And flash memory has some unique characteristics that are important to understand. First, read operations are done at the page level and are relatively fast. Write operations can only change bits from 1 to 0 and also happens at the page level. And I note that you cannot overwrite data directly in SSD. Instead, to write new data, you must first erase the target space by using erase operation. Erase operation resets bits from 0 to 1, and these operations are done by at the block level. Also, each block has a limited number of erase cycles, so flash memory wears out over time. Due to this feature, it's very important to minimize the number of write and erase operations to extend the life of the SSD device. And this table shows the comparison between SSD and HDD. Especially, you need to focus on comparison for the performance and cost. As you can see, even though SSD is more expensive than HDD, it can achieve faster I/O speed compared to HDD. So this is the reason why SSD becomes a popular secondary storage in modern computer systems. And SSD utilizes a special abstraction layer called Flash Translation Layer, or FTL for short. Basically, the file system handles I/O requests by sending block level operations, such as reading or writing a block. But SSDs don't natively support this block. The blocks in flash memory are different from the blocks assumed by the file system. In addition, SSD exposes several low-level operations like read, write, and erase operation at the flash level. And the file system doesn't support these low-level operations of SSD. That is, there is big mismatch between file system and SSD. So to make these components comparable, the FTL makes a flash memory look like a regular block device to the operating system. That is, it manages the mapping between logical block addresses and physical flash locations. And thanks to the FTL, the operating system can just issue standard read and write requests without worrying about the internal details of flash memory. This is the benefit of using FTL. Okay, then that's all for today's class. If you have any question for this lecture, please ask me your question through our Slack channel or LMS system. Okay, then thank you for your attention. Then I'll see you next class.